Так. So today we will continue with the detection of radionuclides and with the further lecture will be on the destructive analysis of radionuclides. So again, we can detect the ionizing radiation of radionuclides and what we're interested in only by the interaction of this ionizing radiation with matter. It's the only way to detect it. And we will start with the liquid scintillation counting because it is the most efficient way to analyze the beta emitters and alpha emitters. So what is the principle of the liquid scintillation counting? The radionuclide that is located then in special scintillating cocktail excite the solvent molecules for this cocktail. Solvent is usually presented by aromatic organic molecules like toluene or pseudocumin or other molecules. These excited molecules of solvent then transfer energy to the special organic molecules called scintillator. The scintillator transfer energy to the visible light, and this visible light then detected by a photomultiplier tube. So it's just a brief scheme, general scheme of the liquid scintillation counting. And then we have at least two possible negative processes that we will talk a bit later. So, usually the radionuclide is put it in the scintillation cocktails as a liquid solution of the radionuclide, aqueous solution or organic solution, or it can be any kind of, for example, it can be a special resins where you sort radionuclide and you can put it in a liquid scintillation cocktail, or it can be filters with adsorbed radionuclides. So again, this is again a representation scheme of the process, excitation of solvent molecules, then transfer of energy to the scintillator, and then emitting all the light. You will have all the presentations, and you will see all these structure formulas if you need them. There are several kinds of scintillators that are inside of the scintillation cocktail. They called primary scintillators and secondary scintillators. And the reason to add a secondary scintillator is to shift the wavelength of the emitted light for better, let's say, efficiency of the capturing the light by a photomultiplier tube. This is the main reason for adding the secondary scintillators. The primary scintillators, they're quite effective in light emission, and the secondary scintillators, their purpose is shifting the wavelength of the light. And this is a general scheme for the liquid scintillation counters. They can be with different design, but let's say the most popular ones, like 3-cup spectrometers, they have this scheme. So this is a vial where you put the liquid scintillation cocktail with the radionuclide, and you have two photomultiplier tubes. In some cases, in some simple devices, I would say, where you don't need very low background for detection, they have only one photomultiplier tube. But in addition, the second tube will help to decrease the background of the measuring. Why is so? In general, photomultiplier tube generate so-called the dark current. So they there is some noises, some noisy signals that are generated by by tube itself, and all the signals goes then to the analyzer, and you detect them, and you can be confused with them as a positive signal, but it's not correct. So when you add the second multiplier tube, then you have so-called the coincidence scheme. That means that only signals that are coming from two multiplier tube in one time, in just a short range of time, they will be summarized. Otherwise, if there is only one signal from one photomultiplier tube, this signal will be neglected. So this helps to neglect these noises from the multiplier tube themselves, and this helps to decrease the background of the measurement. Yeah, this high voltage goes for to work for multiplier tubes, and then the signals from this coincidence scheme is going to multi-channel analyzer, and multi-channel analyzer separate signals as it was yesterday in the lecture. It's the same principle that depending on the height of the impulse from this electronic scheme, you put your signal in one channel or another, depending on the initial energy that was transferred to the scintillation cocktail. So the relationship is quite simple. The higher the energy of the beta particles or alpha particles that are emitted. So the higher the number of photons that are generated in liquid scintillator, and that means the higher the current pulse in final electronic scheme. So that means, and then this goes to the special channel. So that means that there is a linear proportion between linear relationship between the energy of the particles, alpha particles or beta particles emitted, and the number of channel in the spectrum. And yeah. And yeah, this is a typical view of these vials that are used for liquid scintillation counting. They can be plastic vials or glass vials. And this is a typical spectrum that obtained with this technique. And what is, again, interesting, maybe, that when we are measuring, so the energy of beta particles that are emitted by radionuclides is usually in the range from 18 kiloelectron volts for tritium, it's the lowest energy, to, I don't know, 200 to 300 maybe maximum kiloelectron volts, to 3,000, sorry, kiloelectron volts. So, but alpha particles that are emitted, they're usually in the range of 4 to 7, 8, maybe 9 megaelectron volts. So that means that in principle, the energy range of beta particles and alpha particles, they're different. Beta particles have lower energy in general than alpha particles. But this is a spectrum for alpha and beta particles. This is a beta spectrum, and this is alpha spectrum. And we can see them, alpha particles and beta particles, in the same range. Then why? That is because alpha particles, they generate 10 times less photons in liquid scintillator than the beta particles. There are several explanations for this phenomenon. One of them that alpha particles have lower range. That means that they excite less molecules. That means that they produce less photons. And another explanation that alpha particles, they produce a local heat increase. And if you increase the temperature of the scintillator, you will decrease the yield of the photons. So this like a parallel maybe processes that you excite less molecules, and also you decrease the yield of photons. And in summarizing, it results in 10 times less photons produced by alpha particles than by beta particles. That's why we can see. So, and as far as it's a linear relationship between the number of photons and the number of channel, that means that for our analyzer, alpha particles look like beta particles, not beta particles, but particles with energy with 10 times less energy than they have actually. For example, alpha particles with the energy of 5 mega electron volts will look like particles with the energy of 500 kiloelectron volts. And this is range for beta particles. Yeah? That's why we can see both alpha particles and beta particles in the same energy range when we use liquid scintillation count. And again,
excuse me.
Yeah.
I think you looked at books fixed microphone. That's one online.
We changed yesterday this scheme with microphones, and now we have microphone from webcam, and they should hear us. At least it was indicated that microphone is working. I think that they would somehow say it. Yeah. Okay. So, and again, remember about this conversion electrons. It's not really visible from here, I guess, but there is a spectrum, beta spectrum, and then this very sharp peaks that can be confused with alpha particles, but it's not alpha particles, it's conversion electrons. So it's important to remember about that. And again, it's typical spectrum, beta spectrum for carbon-14 and for strontium-19. That is in equilibrium with yttrium-90. So, if you if you will use this linear scale of energy, it's not really representative. But when you use the log scale of energy, then you will see this two not really just separated peaks, but you can clearly see the difference in energy. There are several softwares that are dealing with the deconvolution of this spectrum, but it always, or in the case of liquid scintillation counting, it always better to have a pure radionuclide beta. You can have a mixture of alpha and beta emitters. And yeah, okay, so it's another example with the conversion electrons. Yeah. Okay, then, and now it's about the quenching of the light that is emitted or not emitted by the scintillator. So there are two types of quenching. First type is the chemical quench. What does it mean? It means that on the way of transferring energy from the solvent molecules to scintillator, there are another molecules who are capturing this energy, but doesn't produce light at all. So it can be like organic compounds containing halogens, like chlorine or bromine, or it can be like nitro, methane, or some other organic molecules. So they can catch this energy, but they convert it to the just vibrational modes, so like let's say heat production, but not the light production. And that's why in this case we produce lower numbers of photons. And again, for our analyzer, it can mean like it can have two meanings. One meaning is that we have particles with lower energy. That's why our peak will shift to the lower energy range. And our analyzer can think that we have a less radionuclide, less concentration of radionuclide. So we are losing in the efficiency of the detecting of radionuclides. And the second type of quenching is color quenching or physical quenching. That means that even if all the energy is transferred from the solvent molecules to scintillator and the light is already emitted, but on the way between the scintillator and the photomultiplier tube, there are some colored substances, iron or chromium or other metals or organic molecules, colored organic molecules, and they catch this light, and again they just absorb this light without emission any other lights. And again, we lose a number of photons with all the consequences. Yeah, shifting the peak position and lowering the peak square. So quenching, yeah, again an example how peak shifting. And there are several methods to take into account this quenching. So to correct the quenching effect, yeah, again, it's not very good resolution of the present. So anyway, one of the simplest way is the addition of internal standard. That means that we measure our sample, then we add the known amount of the same radionuclide, and then we can estimate how much, what is the efficiency of our measurement, and we can recalculate what we measured to the real activity. It is the simplest way, but it's very time-consuming. You have to add in every vial the known amount of radionuclide, so it's not very convenient. Another way is again just very simple procedure. It's analyzing this channel ratios. So if we have this spectrum, we can divide all this energy scale on two windows. A, B. So, and we measure the standard solution of our radiant light without any quenching, it's pure solution without any quenches. And we can calculate the square here, and square here. We can calculate this ratio. And then we can add by ourselves a quencher, any quencher that we would like. And then we will change spectrum. So it will be a shift spectrum. And you will have another ratio. Yeah? Now you have, let's say, sorry. So, and you will know the efficiency of the detection of your radiant lights, efficiency 1. And doing this step by step, you will obtain this graph. So it's just the relationship between efficiency and this ratio. Yeah, I maybe not really nice relationship because it will with so it will be like this. So your efficiency will have several experimental points, and when you will measure your radiant light, your solution, you will get some error value, and you will get this efficiency. Again, it's very simple, but you have to do it for any kinds of radiant light. So if you have several radiant lights for each type of radiant light, you have to do this because every radiant light has its own spectrum. And, yeah, you have to do it several times. So it's again simple procedure, but not like very often convenient. If you measure only one radiant light, maybe it's okay. But if you have a lot of them, it's not so easy. And yeah. And there are another procedures that are already in use in many equipments, commercial equipments. They are already in there. So it's spectral indexes of this sample, or even better, the spectral indexes of external standards. What does it mean? That means that we have what is the external standard? You remember this scheme, this our wire, this photon multiplier tubes. And then to measure the quenching properties of the solution of this cocktail, the external standards is coming in the bottom of this wire. external standards, it's usually either European 142 or can be radium 56 or can be barium 123 or depending on the register. And this external standards emits gamma rays. Then, as far as the liquid scintillator, it's an organic solution with low efficient atomic number. That means that the main process of interaction of gamma radiation with this matter is the production of quantum electrons. So this is quantum electrons. And these electrons, they produce some spectrum of quantum electrons. It is something like this. It's not a single peak or a single energy, it's different energies with some maximums. And by analyzing this spectra, so not with two needles, but with several windows, a ratio between them with different weight factors, the analyzer gives us this parameter, transformed spectral indexes of external standard. Then, again, we can do the same procedure as before for this simple technique. Construct this graph of dependence of efficiency with this parameter. And what is important that this parameter is like universal parameters for radionuclides with the same energy or close energy. We can use it for different radionuclides with close energy. And also, when we look on this parameter, it's not really clear visible from your side, but the main effect on the efficiency of measuring the radionuclides is visible only for radionuclides like tritium with very low energy of beta particles, because they produce too few photons, and any quenching of these few photons will have a great effect. Even for carbon-14, it's already not such a drastic effect. But carbon-14 has energy like 150 kiloelectron volts, so not very high energy, but still only at very. So I forgot to tell you that the higher the value of this parameter this year, the higher the efficiency of the detection. So if you have very low value of this parameter, that means that you have very bad solution. And there are a lot of quenchers, a lot of different contaminations, etc. For alpha particles or for high energy beta emitters, usually you have the efficiency around 100%, let's say 98–99% of efficiency of measurement. Only for such a low energy beta emitters you have efficiency ranging from, let's say, 40% to 68%. And that is important for us because such in beta emitters, they are called difficult to measure radionuclides, and they represent the main difficulties in characterization of radioactive waste. If you have fewer beta emitters, and then you have a lot of problems. And again, as far as we put our radionuclides in the solution, that means that they have to be pure, and that means that we have to prepare this counting source very carefully. And we will talk about it in the next slide. Yeah, this is again this dependence of this parameter and efficiency. And you see this how it is important for tritium, maybe important for carbon-14, and then almost not important for alpha emitters like plutonium. And sometimes if you have alpha and beta emitters immediately in your solution, for example, even if you want to measure the gross alpha and beta activity of water solution, for example, you can use so-called alpha-beta discrimination. It is done by electronic steam of the spectrometer, so you don't need any separation, chemical separation, because there is a dependence on the time of this pulse, and you see that this excitation produced by alpha particles lives longer than excitation produced by beta particles, and you can adjust the time when you, in simple words, stop measuring the signal and then start to measure it again. Yeah. More real. So you have the same picture. So you have this pulse from beta and this from alpha. There is time, measurable time, and you can put this or set this discriminator and say that everything that we measured in this period of time is related to beta emitters, and everything what we measured after this time is considered as a alpha emitters. And then you will get two spectras. But it will be the same picture as it was before. Yeah, it will be like this. This spectra is produced by this alpha beta discrimination. If you have, if you set this time not correctly, then you will clearly see it, because you will see small peaks in this region for beta spectrum, and you will understand that it comes from alpha particles. So you have to adjust this time discriminator in another range. But it's a rather simple procedure again. But again, you have to do it for not each pair of alpha and beta emitters, but for, if you know the energies of alpha and beta particles that are emitted, and they're the same for another pair, so it will be the same time discriminator, more or less. So it depends on the energy of this alpha and beta particles. And again, the Cherenkov counting is very usable technique, very useful technique, because there are several radionuclides, pure beta emitters, that you can measure without addition any scintillation cocktail. And the Cherenkov counter have several advantages. First of all, you don't need any liquid scintillator cocktails. That means you don't produce the organic waste. Also, there is no chemical quenching because there is no solvent that transfer energy. The light produced just by particles that are emitted. And there only can be a color quenching. If you have the colored solution, then probably you can have this color quenching. But again, you can estimate the effect of this quenching by these graphs of efficiency versus some parameter. Okay. And you can see that for some radionuclides like yttrium, the efficiency of the detection can be very high. And again, without any liquid scintillator, organic scintillator. This is just an example of different spectrometers. I think one of the most popular is produced by Elmer. That's called 3-carb with different series. It can be a low-level counting or with some additional features. And there's a Finnish company, Hydex. They produce these simple counters. They're mobile counters, or this more or less modern, let's say, counters. Previously, it was also very low background counters Quantulus, if you know it. And nowadays it doesn't produce it anymore. I don't know why. Because it was a very good spectrometer and with very low background. And nowadays the Perkin-Elmer also produce so-called Quantulus spectrometers, but they're not so. Huh?
I use this one.
Okay, this 3-carb. Yeah. Do you remember the model?
No,
2710 or 2810?
I think.
And yeah, nowadays the Quantulus also looks like this. Spectrometer. Yes, yes. Sorry?
We also have one we don't use even used in the medicine faculty, and then they donate us.
Mm-hmm. And there's an example of using the solid scintillators for to make let's say mobile detectors that you can bring anywhere. You just need this scintillator detector. It's a plastics, and this photomultiplier tubes, not tubes, it's a semiconductor photomultiplier diodes. They are very compact, but the drawback of them that they're quite noisy. So the vacuum tubes are better to use for low level countings. But if you have like a intermediate level waste or whatever with relatively high activity, then you can use even this noisy diodes and take this detector anywhere. Yeah, alpha spectrometry with semiconductor. It's if you will look on this spectra for again for liquid scintillators, you'll see that the resolution, energy resolution, is not very high, and it is difficult to separate different peaks of different radionuclides. But semiconductors, they have very good resolution. You can separate the peaks produced by different radionuclides with very high resolution. So it's high is a relative word, depending on what you are measuring, in which energy range. For example, you you saw yesterday the gamma spectrometry, and the resolution there was something like 2 kilo electron volts, and it is very nice. But because gamma quantas has energy again from 50 to 3,000 kilo electron volts. But again, alpha particles have higher energy. That means that for them the resolution of 30 kilo electron volts is okay. So it is high. 30 kilo electron volts for gamma spectroscopy is bad resolution, and for alpha spectroscopy is good resolution. So again, the good resolution is a relative term depending on what you are measuring and what the energy you are measuring. And this is an example of, let's say, perfect alpha spectrum. And to measure alpha particles, you have to use the special cameras that are vacuumed, because again, we remember that alpha particles they have a short range, and they absorbed by air, just by air. And if you have some space between your source and the detectors filled with air, you will see no alpha particles, because they all will be absorbed by the air. So that's why we need the vacuum in these cameras. Also, there's effect of pressure of the vacuum on the spectrum of these alpha particles. The higher the higher the content of the air, let's say, in chamber, then the worse the spectrum resolution. And again, as far as the part of the alpha particles are absorbed by air, and also when alpha particles moving through the air, they are losing part of their energy. That means that we will have a shift in energy when we are measuring alpha particles. That means that, again, you have to calibrate your detector for a certain pressure in your chamber. It's very important when you need to detect different radionuclides. And another important point, that you must not use the high activity in these chambers, because again, yesterday we saw that the energy of the recoil nucleus in the case of alpha particles is very high. That means that recoil nucleus can go from the counting source to the detectors and will stay there forever. You cannot remove them by this chemical treatment or whatever. And as far as many recoil nucleus, they are also radioactive. That means that you will have a very high background when you will measure next samples. So with time, all these detectors, they're degraded by the recoil nucleus. Either you will change these detectors every month if you will have high activity, or if you will use not, let's say, low activity, it can last for years. Yeah. But again, these detectors, they are not so expensive, the detectors itself, because it's just silicon, pure silicon, not the germanium. Yeah, so it's not so expensive. You don't need any cooling of these detectors, and the voltage is only around 40 volts, so there's no high voltage applied to these detectors. So it's a rather simple electronic scheme. And to obtain this nice peaks, unfortunately, again, you have to perform a lot of chemical procedures, accurate chemical procedures, because if you have a thick source of your alpha emitters, then you will have not a sharp peak, but this peak with tails. and this tail can be very big. And if you will have several alpha emitters with these big tails, you will hardly separate them, and it will be very difficult to determine their activity, because it will be like superposition of these tails, and it will be difficult to analyze them. So to perform, to obtain these fin sources, you can use either electron deposition. So it's typical scheme of the devices used for electron deposition. You have a stainless steel here. It is a cathode, and you have a platinum anode, and you have a solution here. And during the electron deposition, you will get this thin layer of your radionuclides on this stainless steel. It can be not only stainless steel, it can be nickel or titanium, or whatever you prefer. And then you just remove the solution and dry this disc, and you can measure your radionuclide. Or there's no. Okay. Then there is an example of the spectrum of the radium obtained with the semiconductor detector and with liquid scintillation counter. Just as an example of the difference in energy resolution, that with semiconductor you can distinguish even such a close peaks and determine the activity of the daughter radionuclides. And this is a typical view of different alpha spectrometers. It can be separated chambers, so they can be put it in racks, dependent on the budget of the organization. There are other techniques that can be useful for alpha analysis on the distribution, on the analysis of the distribution of alpha particles or beta particles. There is track analysis, alpha track analysis. So you have your sample, solid sample. You put plastic detector on it. And after a certain time, you remove this detector and analyze the tracks that are produced by alpha particles. It is useful when you are looking for hot particles, or when you investigate in the inhomogeneity of the radionuclide distribution. This is done with a plastic detector, or they can be used only once, or you can use this digital radiography. That means that you apply not the plastic detector, but it is the detector covered with special composition. It's usually europium bromide, europium 2 bromide. No, it's with the composition. So it contains europium 2. But the main composition, it's barium bromide fluoride, and then it is doped with europium +2. Yeah, and europium +2 under action of ionizing radiation excited, and then you irradiate it with red light, and you produce emission of another light, and you detect this secondary light. And again, you will obtain more or less the similar picture of the distribution of radionuclides, and also with this technique you can distinguish between alpha and beta particles that are irradiated. Yeah, this is all for the measurement of the radionuclide. The next lecture will be on destructive analysis. We can have a short break if you like, I guess. Yeah, okay. Then we will have a short break.
Ah, okay. I see. I mean, it's space time.
So let's continue with the destructive characterization of radioactive waste. Yesterday it was practical test, and later it was a non-destructive characterization, and you saw that mainly the gamma emitters can be characterized or analyzed by these techniques. Because they have the gamma rays have high penetration ability, and that means that they can be released from the container or from the material and can be detected. But in the case of pure alpha and beta emitters, you cannot use just the gamma spectrometry because you have no signal in this case. So we have to prepare the counting source from the our material, and there are several steps before we can measure these samples. So first step is of course sample, let's say preparation, like homogenization. If you have soil or concrete or whatever, it's an inhomogeneous material, or you can dry it, but then you add also tracer. Tracer is needed to calculate the chemical yield of all these separation procedures, because in every step you can lose part of your radionuclide, and tracer will help you to understand what part did you lose and to recalculate the chemical yield of all these procedures. So after this homogenization and tracer, addition of tracer, you either reconstruct, like by drying the liquid samples, or dissolve the solid samples. And after this procedure, after obtaining the solution, aqueous solution that you can handle further, you separate your radionuclide, because usually again we have either difficult to measure radionuclides or radionuclides that have similar spectra, and we have to separate them either from bulk matrices that will, for example, in the case of alpha spectrometry, if we didn't remove a lot of salts, we'll get a thick sample, and we will have all these tails on the spectrum, and it will be very difficult to analyze the spectrum. So after the separation of our radionuclide, of our target radionuclide, we prepare a counting source and finally measure the sample. So about measurement, we already talked, and now we'll talk about all these procedures before. First of all, we need to, as far as destructive analysis, we need to destroy our sample, either dissolve it by different methods. And why do we need it? Of course, for destructive analysis, then we have to perform destructive analysis in the case we have this difficult to measure radionuclides. And it can be different kind of samples, not only solid samples, yeah, in the pre-treatment procedure. In the case of liquid samples, we have to dry them. How we dissolve the solid samples? It is either the acid leaching, when we put acid, heat it, and try to reach all the target radionuclide. It can be just etching or incineration. It can be UV-assisted oxidations in the case of organic compounds, or it can be these two procedures. They're very effective. It's microwave digestion and fusion. Fusion. Oops. Fusion is for fusion you can use Catanac's equipment. It fused your solid samples with different fluxes. Depending on the type of your samples, you can use different fluxes, and it is more or less guaranteed that all your sample, depending on its type, will be dissolved. It's very efficient, but unfortunately, it works only for small samples. Yeah? So if you have very active samples, it's not a problem. But if you have like low-level waste or natural samples, then it may be not very suitable. Because again, you have just grams maybe of the samples, and it can be not enough for further measurement. But again, if you have enough activity in your solid samples, then you can easily dissolve it with this procedure. Okay, so I have to check the presentation, sorry, because I think it's not the last one. Yep. Sorry for that. It's not the last version. I will check it. Yeah, here we go. This is the equipment itself for fusion procedure, where you melt, you fuse your sample with the flux. Again, or you can use the microwave digestion. It is more suitable for larger samples. You can use either the open vessels or closed vessels for hydrothermal treatment. With microwave digestions, again, it takes only minutes for the dissolution of samples. Of course, you cannot use very large volumes like 1 liter glasses in the lab and use acid leaching. But nevertheless, it is higher or larger volumes of samples can be used in the case of microwave digestions. But it is not. It can be not so effective for dissolution of complex samples, like, I don't know, soils with a lot of silicates or other materials. So it's always a balance, as Michael Ogeron showed you this picture with a balance in man. It is the same here. And acid digestion, of course, it is maybe the simplest way, maybe not the most efficient way, but the simplest way to dissolve solid materials. So just take your samples, maybe not 100 grams, but tens of grams of acid, close it with the glass and boil it until all your samples will be dissolved. And for different samples, again, you can use different acids or combination of these acids, like nitric acid plus hydrofluoric acid, etc. And don't forget about traces, because again, they're helping us to determine the chemical yield of all further steps. It can be like usually you use isotopic traces. That means that you add the isotope of the same element, if it is possible. If it is not possible for some reasons, then you can add the chemical analog. For example, for americium, you can use either europium or curium as an analog. They're all trivalent. They have, in this case, the similar behavior. So it is more or less approved that you can use these chemical analogs. Not always, but sometimes you can use it. Yeah, this is just an example of the traces for actinides that you can use to measure the chemical yield, and these red peaks are related to the traces, and the blue ones is for the actinides that we would like to analyze. So with alpha spectrometry, you can have such a nice peak resolution, but you have to prepare very thin samples to measure. After that, we need to, when we dissolve our samples at traces, then we need to separate our radionuclides. And there are several methods to do this: precipitation, ion exchange, or chromatography, extraction, and maybe in some cases gas absorption. But in all these procedures, you always have this two-phase heterogeneous system, and that is the force that move that led us to separate radionuclides. It's always the distribution between two separated phases, either liquid-liquid in case of extraction, or liquid-solid like precipitation and ion exchange, or gas-solid as gas absorption or sublimation. Yeah. Why do we need to separate? Again, either we remove all the matrix that will have negative effect on our measurement, or we remove the interferent nuclides. Some of the daughter radionuclides they can interfere with our measurements. Yeah. And finally, for preparation of pure counting source. So let's start with precipitation. Again, it was already mentioned in Professor Ojavan lecture, but just to remind you that when we precipitate the solids, we have to take into account the solubility product of this precipitate. If we have this multiplication higher than solubility product, then we will get precipitate. If not, then we will have no precipitate at all. And yeah. And this is an example when we don't have a precipitation, even if we have a high activity of radionuclide. And just a simple example, if we have 1 megabecquerel per liter of silver 105, we can recalculate it with this law of radiochemistry, where activity is equal to lambda m, etc. We can calculate the concentration of silver from this activity. And we know the solubility product of silver chloride. There is a table with solubility product, where this again solubility product, and that means with this solubility product and with this concentration of silver, that even in the presence of 10 molar hydrochloric acid or fluoride salts, like lithium fluoride can be, we will not form precipitate at all. But from the school chemistry, we know that silver is precipitated with fluoride, bromide, iodide. But in this case, we don't reach the solubility product of the silver fluoride. So to precipitate the silver, in this case, we have to add the carrier. In this case, it's quite simple. We just put the stable silver salt, like silver nitrate, and we can precipitate the radioactive radionuclide of silver with the stable radionuclide. So the precipitation of our radionuclide with other components called co-precipitation at carrier. And carriers can be of different nature. It can be isotopic carrier, so it's the same element, but another isotope. It can be stable isotope, like in this case of silver, or as it was an example about this metastable state of barium with 3 minutes of half-life. And we can add barium, stable barium to precipitate it. It's the same isotopic carrier. It can be a specific but non-isotopic carrier. That means that we add the stable element with the same chemical properties. It's like the case of co-precipitation of radium with barium sulfate, or as I told you before, it can be a precipitation of, for example, americium with lanthanum fluoride or oxalate or whatever. So it's another element, but with the same chemical properties. So it's non-isotopic carrier. but specific. And it can be non-specific, non-isotopic carriers. So that means that we co-precipitate our element with absolutely different chemical properties. It is like co-precipitation of actinides with iron hydroxide. Iron is absolutely different than chemical properties from actinides, but still it is a very efficient way to co-precipitate actinides with either with iron hydroxide or with the manganese dioxide. So it's a very efficient way. So, and again, the goal of to use the precipitation method is removal of interferent radionuclides. We can precipitate only the elements with the certain chemical properties. It is separation from the sample matrix and or the pre-concentration of our targeted radionuclide. There are several examples of the carriers for nuclides and a bit more of these. So if you have any certain interest of certain radionuclides, you can look directly in these tables. And this is an example of the preparation of counting source for alpha spectrometry by using co-precipitation. So in the previous lecture, it was an example when we use electrodeposition of the radionuclides for alpha spectrometry. And this is another technique when we use special filters that are saturated with some salts like cerium fluoride or barium sulfate. And when we filter the solution through these filters, we can separate and pre-concentrate the radionuclides like trivalent actinides, so uranium or plutonium, and we will get a very thin layer on these filters, and we can then use it directly for alpha measurements after drying, of course, not just after filtration, just drying a bit, and then just put it in alpha camera. So it's a very convenient way to prepare the source for alpha spectrometry. Again, it's pros and cons. It's not quite, but more expensive way to prepare this counting source for alpha spectrometry, but it's much more convenient than electrodeposition and much faster. So when we look on the precipitation, there are several pros and cons. It can be very selective. We can choose only elements with the specific chemical properties. If we put carriers, it can be a very high degree of precipitation and concentration. Rather simple and convenient. I mean, everybody who once did chemistry can do this precipitation and filtering. And of course, it can be scaled up because, again, you can separate the precipitates quite easily, even from the huge volumes of our liquid samples, for example, like hundreds of liters. But it can be time consuming. We have to wait when all the precipitate will settle down. Sometimes we need to use large amounts of carrier, and that will generate radioactive waste afterwards. Nowadays, it's not very technological because, again, you have to perform several procedures to extract your radionuclide, and yeah, you can contaminate the area around your workplace, and you will produce again the radioactive waste by using these carriers. So other methods for radionuclide separation and pre-concentration is a solvent extraction or liquid extraction, the same term but used by different authors. Solvent extraction is used in wide areas of applications in different kinds of chemistries, for organic chemistry, analytical chemistry, and of course in the technology, hydrometallurgy, reprocessing of spent nuclear fuel, etc. But we will use it for extraction of our radionuclides. So solvent extraction is the distribution of the component between two immiscible liquids, and organic liquids can be lighter or more or heavier than aqueous solutions. So it depends on your system. It's not always that organic phase on the top of this mixture. And yeah, you just add organic solution to your aqueous phase, contact the phases, and then separate the phases with your component in organic phase. And just again, to use correct terms when we are speaking about solvent extraction. When we extract our component, then the organic phase called extract, and the remaining aqueous phase called raffinate. And then we back extract or strip our solution, then this aqueous phase called back extract. So, and if we have, we use extraction in the case of one component when we want to concentrate, for example. And if we would like to separate elements, then in one step we can use scrubbing. That means removing the interferent component from the organic phase by washing the organic phase, or by scrubbing the organic phase with special aqueous phase containing some maybe ligands or another acidity or whatever. And there are several mechanisms for liquid extraction. It's physical redistribution. It can be solvation by organic extractants, or ion exchange, cation or anion exchange. The physical distribution is very simple to understand. It's just that the one component is more soluble in organic phase than in aqueous phase, and it's the most famous example of iodine, of molecular iodine, that is more soluble in toluene, for example, than in water. I think many of you did this experiment maybe in school or in university. So it's again very simple mechanism. Then we have solvation mechanism. That means all ions that are present in aqueous solution, they're surrounded by the molecules of water. So they have this shell. In aqueous phase it's called hydrated shell, but in general when we speak about another solvents, then it's called the solvated shell. And we can use specific ligands which, let's say, remove the molecules of water from the hydration shells of ions and replace them by themselves by these extractant molecules. And this makes the ions or salt is soluble in organic phase. So in principle, this salt, for example, europium nitrate, something like this, is not soluble in kerosene, for example. But if we add a specific extractant who will remove water molecules from this surrounding of europium and nitrate, then it become soluble in organic phase. This salt becomes soluble. It can be the same mechanism when we extract some specific halogenated acids. In this case, it's called hydrate solvate mechanism. And yeah, there's just an examples of typical extractants which are used in this case. It's TBP, the most famous extractant because it is used in Kurz process in reprocessing of spent nuclear fuel. It is trioxyphosphine oxide, very often used in radioanalytical applications. It methyl isobutyl ketone, also used in some industrial processes, and triethylamine. Then there is another examples of these extractants that are used for alkali and alkali earth metals, crown affairs and calixarenes, and it is very interesting molecule because as far as they're organic, you can modify them in many ways to adjust their properties, their selectivity, their efficiency, their ability to be bonded to sorbents or whatever. Then there is an ion exchange mechanisms. First, cation exchange mechanism. In this case, the extractants is organic soluble acids. Just an example of general formulas of these extractants. And the process that is lies in this mechanism is the exchange of the proton of this acid by the cation of the metal. So that's why it is a cation exchange mechanism. Proton is the cation and the metal cation exchange this proton from the acid. So it's just like a normal equation in inorganic maybe chemistry when we exchange one proton one cation with another, and so why I read here this molecule as a dimer, because usually organic solvents they are non-polar solids, liquids, and there is a law that similar compounds dissolve in similar solvents. That means that in non-polar solvents, molecules will dissolve only in non-polar modification, let's say. If we will look on the structure of this, all these organosoluble acids, we will see that there is a negatively charged end with oxygens and positively charged parts with the phosphorus or carbon and all these radical substituents. That means that it is like a dipole, and it is a polar molecule. That means that polar should not be dissolved in non-polar diluents. But in case of the in these acids, they can form such a dimers with the hydrogen bonds, and now we have a non-polar molecule because it's like balancing the charges. And in this form, these organosoluble acids will be dissolved, can be dissolved in organic solutions. So they present in non-polar diluents as a dimer. That's why we read this equation like this. The drawback of this mechanism that there is a release of proton in aqueous phase. That means that during the extraction, we will increase the concentration of protons in aqueous phase, or concentration of acid, strong acid in aqueous phase. And we remember, I hope so, that organosoluble acids, they are weak acids. They are weaker than the normal mineral acids like nitric acid or hydrofluoric acid. That means that if we increase the concentration of mineral acid in aqueous phase, then we decrease the efficiency of this process, because we change the way of the reaction from left to right to right to left. So then all the metals will be back extracted to the aqueous phase. That's why in these systems we have to keep the value of pH of aqueous solution constant by adding buffers or by adding constantly some ammonia solutions or some other basic solutions. And again, this is just typical examples of extractants that are widely used in radioanalytical applications and in industrial applications. First of all, it is this HDHP, phosphoric acid, or this phosphonic acid. So it is the same substituent to ethyl, but here there is a direct link between phosphorus and carbon atoms, and of course it's just carboxylic acids. Another ion exchange mechanism is anion exchange mechanism, and in this case we exchange anions like technetium perticnetate anion, or complex anionic forms of radionuclides, lanthanides, and actinides. And then in this case, we exchange the counter ion of this organic basics with these anions. So it's more or less the same as cation exchange, but anion exchange. And this problem that we can sometimes see by using liquid extraction. If we have very high loads of organic phase, we can reach the limit of the solubility of these complexes of metals with organic extracts, organic ligands, and we will produce, let's say, precipitates in organic phase, and they can be hardly separated from organic phase or aqueous phase. So we should avoid the formation of these third phases. That means that we should not use very concentrated solutions of metals, or if there are a lot of metals coming from matrix of our samples, it can be tricky. It's just an example of most important parameters that we use for describing the process of liquid extraction. First of all, it's a distribution ratio. That is just a ratio between concentration of our element in organic phase and in aqueous phase in equilibrium. So it's not in initial concentration, that's concentrations when the equilibrium is reached. And if we separate radionuclides or metals or whatever, it is the separation factor. That is the ratio between two distribution ratios of two elements. And usually we put the larger distribution ratio on the top, that the separation factor should be always higher than 1. So just general rule. Yeah, and this are the conditions for effective separation of two species. So first of all, yeah, of course, distribution ratio for one of them should be more than larger than another one. But the multiplication should be around 1. That means, for example, if the distribution ratio of component A would be 1000, and distribution ratio of component B will be 10, then we can say that okay, this condition is correct, but this condition is not correct in this case. So one component should be should stay in aqueous phase. And this is effect of so-called salting out agents. So salting out agent, it's a non-extractable salt with the same anion as an extractable salt, and this is an example of the dependence of the distribution ratio for uranium nitrate with addition of sodium nitrate. So you can see that when we increase the concentration of sodium nitrate, the distribution ratio of uranium is increasing. So why it is happening? There are two, again, possible mechanisms. One is the so-called Le Chatelier mechanisms, when if we put a lot of any component on the left side, then the system will do its best to shift the equilibrium to remove this excess of this component. So that means that if we put a lot of nitrates in aqueous phase, then the system will try to shift the equilibrium to the way that all the nitrates go to the organic phase. And it is possible only in the way that all these nitrates goes with uranium to the organic phase. So it is just shifting of equilibrium. Another explanation is the decrease of water activity coefficient. That means that, again, when we extract our component, we remove water molecules from its hydrated shell, so they're here. When we increase concentration of salt, we decrease the activity coefficient of water. That means that we can say, not directly, but in simple way, that we decrease the concentration of aqueous water molecules. It's not correct, it's just an explanation. So if we decrease the amount of water molecules in this part, that means that a system will try to shift the equilibrium to increase the concentration of these molecules. So in both of this process, we shift equilibrium to the right side, and that's why we increase the distribution ratios for our target radionuclide or our component. And this is a nice example on how different mechanisms can change if we are changing the conditions of the extraction. This is extraction of molybdenum by this phosphoric acid. And in the region of low pH, it is a typical dependence of the distribution ratio, because when we increase the concentration of nitric acid in the system, we decrease the ability of this weak acid to bond the molybdenum. So we decrease the distribution ratio with increasing the concentration of nitric acid. So it's a normal way of the dependence of the distribution ratio. In this region, when we go to the lower concentration of nitric acid or to the higher pH values, molybdenum hydrolyzes. There is a hydrolysis of molybdenum cation, and that means that it cannot be bonded with this weak acid anymore. And in this case, the more hydrolyzed the molybdenum, the lower the distribution ratio of molybdenum. And this is the interesting part of this very complex dependence. With the high concentration of nitric acid, this weak phosphoric acid doesn't work anymore as an acid. And from this point, it serves as a solvate. It's like a tributyl phosphate. It's exchange the water molecules in the hydration shell of the molybdenum, or solvation shell of molybdenum. So we are changing mechanisms from cation exchange to the solvation mechanism. So it's the explanation of such a complex activities. There are several benefits of solvent extraction. Of course, it's rapid. You just need several minutes to reach equilibrium. In many cases, it's very efficient. You can extract in one step more than 90%, let's say, of radionuclide. You can separate radionuclides by applying the selective extractants. Again, you can select the extractants among a very wide variety of different organic molecules. So you can choose the most selective extractants for your radionuclide. Then you can back extract your radionuclide in aqueous phase, so you don't have to deal with organic phase anymore. So there are many technological industrial applications. So you can use it in very large scales. But in this case, usually you have to use toxic or flammable solvents, like kerosene, or there are some fluorinated solvents. They're not flammable, but they're highly toxic. Then you can produce large volumes of organic waste, because back extraction is efficient, but it's not 100% efficient. If you have a complex composition of your matrix, probably you will have to have multiple extraction steps to separate your radionuclide. Then there is another method, chromatography, or we will talk about ion exchange. Chromatography in general is just the dynamic method of the redistribution of the component between the two phases. And it can be gas phase, liquid phase, mobile phase, and the stationary phase can be solid or liquid phase. So in general, it just the chromatography itself, it can be not only ion exchange. But in our case, as far as radionuclides, what we are separating, they present in charged forms. Then we use usually ion exchanges, ion exchange resins or sorbents, and it is a reversible exchange, first of all, of ions. And yeah, again, there are two types of ion exchange: cation exchange and anion exchange. So, and it's a similar way. We have let's say mobile phases and stationary phase. Oops. It's distributed between two phases, like in solvent extraction. Yeah, we can say that it is a one-step solvent extraction. But in case of chromatography, we have these multiple steps of the redistribution. That means it's like we made a lot of single steps of solvent extraction. So it's very efficient way to separate two components because it is a multiple stage process. And yeah, this is an example how it looks like, that two components, they are moving with the same element, with the same speed, but as far as one component is not attracted to the sorbent, it moves faster, and another component who interacts with sorbents moves a bit slower. And there are two main types of the separation of elements. Either it's frontal separation, so that means that we put the solution with two components through the column, and we separate them just in different fractions. Or we sort components on the column, so they're catched by the sorbents, and then we elute components either by the solution that removes these ions with different efficiency from the column, but this solution removes all of these components. So it's very similar to frontal elution. Or there's an element which removes only one component selectively. So another component still stays on the column. And yeah, when we talk about the resins, we imagine this stationary phase, this inert support, the polymeric resin, with some functional groups on it. It can be cation functional groups, so like sulfonates or carboxylate groups, or in case of an ion exchange, it will be quaternary amine groups. So, and the mechanisms of this redistribution of radionuclides is the same as in the solvent extraction. So it's cation exchange and anion exchange. Again, there's parameters that we use to compare different sorbents on the efficiency of the retain radionuclides or to separate radionuclides. So it's more or less the same as for liquid extraction. And the benefits of the ion exchange, that it is simple methods. Again, you just need a column with the solvent and put the solution through the column. Usually it has high chemical recovery, and yeah, there are a lot of different resins that can be applied for wide range of applications. Very often the same resins can be applied in common applications like purification of tap water and for purification of radioactive waste, liquid waste. But the contrast for the ion exchange, that's it has a very low selectivity, usually between two cations with similar properties. It requires very narrow conditions, pH or salt content. And again, when we elute solutions, we generate additional liquid waste, and resins themselves also represent radioactive waste that we have to deal with. And there is a top level, I would say, kind of chromatography, extraction chromatography. In this case, as functional groups, we use the ligands or extractants that we can use also in solvent extraction. So we can choose the very selective extractant, put it on the inert sorbent. So that means that we have efficiency, multi-step efficiency of chromatography plus selectivity of extractants. That means that it is very efficient and selective way to separate radionuclides, even with the similar chemical properties. When we, if we want to understand the mechanisms or the order of extraction and separation, it is the same as for the solvent extraction, because again, we use the same extractant as for a solvent extraction. The only difference that we perform at the separation now in dynamic mode, and it is much more efficient. Yeah, there are several requirements to the inner support for this organic phase. Skip it a bit. I just want to show you examples. And you can use this vacuum box to facilitate the separation. So these are the resins that are put in special cartridges. They can be transported to the customer already in cartridges. It's very convenient but more expensive. Or customers can order just the resin and prepare the cartridges by themselves. So depend on the way how you prefer and what is the budget of the organization. And then you put it in this way to the you connect it to vacuum box and put the solution on the top of the column and open the vessel, and then you the solution go through the column, and all your targeted radionuclide are retained on the column. After that, you can back extract or elute the radionuclide in a smaller volume or in a pure solution to prepare the counting source. And yeah, there are a list of different resins that you can use for specific purpose. If you need to separate a certain radionuclides, you can just look on this table and decide which resin you have to use. So it was previously a 3Chem company. I think they're still 3Chem, but it's part of another company. I forgot the name. Doesn't matter. But yeah, these resins are quite good for separation purposes. And these are just an examples of different application of certain resins. For example, here you can with this resin Dipex, you can separate all the actinides from the solution of near, let's say, not near neutral, but with low acidity from low acidic solution. Sorry. And this is an example how you can separate the actinides between each other and from other components by using the Teva resin, using the more concentrated acidic solution. It's more efficient to retain the tetravalent cations, and the trivalent, it is here, for example, americium, and it is 10 to minus 1 distribution ratio. That means that americium hardly retained by this resin and go through the column without any retention. And this is Teva resin that is efficient for removal of tetravalent and hexavalent actinides together. So it is very convenient to separate, for example, uranium and thorium together from the solution, and doesn't matter what other components are in the solution. Also, after this, sorry. Yeah, after absorption of the uranium and thorium on the column, you can separate them by washing with the hydrofluoric acid and separate the uranium and thorium. So uranium will retain on the column, while thorium will be removed, will be eluted. So it's very simple procedures. You don't need any separatory funnels, big columns or whatever. It is just a simple elution steps. And this is an example of the sorbent with the crown ether for removal of strontium. And it is very efficient for separation of strontium from other alkali and alkali earth elements. It can be separated even from barium. So it is a very nice reason. But the problem, so there are, okay, some benefits first of this extraction chromatography. First of all, it's very selective for separation of radionuclides. You can, in 2-3 steps, you can separate or select, extract your target radionuclides even from the solutions with very complex composition. Even you can separate even the trivalent actinides and lanthanides with this resins if you choose the correct conditions. And nowadays it's state-of-the-art methods, and you can use not only individual nuclide columns, but you can put them also like on each other, on the top of each other, and you can have, let's say, one column with different sorbents at once. And when you put your solution and it goes from through all these columns, you can get the specific the sorbents, the small cartridges with the separated radionuclides already, and you can elute them after that to prepare counting source for liquid scintillation or for alpha spectrometry, whatever. But there are some, of course, drawbacks of the methods. It's first of all, it's quite expensive. all the sorbents. The resin is not stable for a long time. Usually, the producer, of course, recommend to use them once, but actually you can use it several times at least. Check it. Yeah, of course, the efficiency is going down, but for at least 3-4 times it can be used. Yeah, and another drawback that they have a limited capacity, so that means that again you cannot use the concentrated solution of the radionuclides to separate them. Yeah. So, as a summary, all these steps, all this separation procedure, dissolution, reconcentration, separation, we need it for analysis of difficult to measure radionuclides. And for these purposes, we can use precipitation, liquid extraction, ion exchange, and extraction chromatography. It depends on the system that you have. If you have a lot of matrix elements in your dissolved material, then it is better to use at first step precipitation or solvent extraction, because they have very high capacity. They can they can work with big volumes, with big amounts of elements, and then for precise extraction of your target radionuclides, you can use extraction chromatography or ion exchange. The chemical recovery or chemical yield of all these procedures can be controlled by tracers, or I prefer tracers, not gravimetry, because tracers you can easily measure them gamma spectrometry or alpha spectrometry together with your target radionuclides. Extraction chromatography, again, it's a very efficient way to separate radionuclides. And as I told you before, this precipitation and solvent extraction often used as a pre-separation step. And in the case of extraction chromatography, you can use the vacuum box to facilitate the separation of radionuclides. So there is actually a short overview of different methods, of different mechanisms of these methods to give you just an idea how we can separate the radionuclides from our radioactive waste, so the dissolved radioactive waste. It is again the case only for when you need to measure this difficult to measure radionuclides. That is very often the case. Sorry for that. Okay, this is all for this lecture, and now we have a lunch break. Yeah, if you have a question.
One slide before you roll the resigned that we can separate the strontium. What is new? Do we remove all the radioactivity or not?
Only strontium, yes.
Yes, but if you have strontium 19, you also have yttrium 19.
Yeah, you separate them.
You separate both of them.
You separate only strontium. Yttrium stays in the solution. But
Yes, but in the radioactive too, with higher energy.
what do you mean?
Yttrium.
Yttrium
Stays in solution.
in solution, yes.
And it has higher energy than strontium.
Yes.
Yttrium is also radioactive.
Yeah. But you need this resin is used. For example, you have a solution that contains a lot of
Because I think
cesium and strontium together.
This resin is not effective to remove all radioactivity from.
Not all. It's only for strontium.
For strontium.
Yes. It is for analytical purposes. It's not for the removal of radioactivity. Because again, if you have
Yes, but the strontium will produce more yttrium.
yes, and you can measure it afterwards. Because if you have a solution that contains cesium and strontium together, for example, and then you cannot measure strontium by distillation or by other.
Yes, we know.
So you have to separate strontium. You separate it, then remove all the cesium and yttrium also, and then you have your strontium solution by emission or by emitting the strontium. And then you measure it. You can measure it directly, or you can wait until yttrium will be converted as well and measure them together. Yeah. So, but it's not for removal of all the radioactivity. It's only for analytical purposes.
But this is very probably with this pair that you have current and
To remove strontium and yttrium, you can use, for example, precipitation with oxides. Both of them are soluble. Just take them.
I thought sources.
Mhm.
Are you using only precipitation methods or
Both.
you are not using electric deposition
We use the electric deposition
after saccharine extraction?
after. But yeah, electric deposition is very cheap way to produce discounted source. But recently we are starting to use more and more these filters because it's very convenient.
For you can use precipitation for all
But alpha emitters mainly ectinites.
yeah.
So, and yeah, we can use this filters or precipitation of
deposition make for other methods make more secret and we take in state.
so electric
No,
deposition.
they are used I use electrical position because I get very accurate results because it's very homogeneous. You can prepare very
But
homogeneous.
maybe, for example, we made polonium
We can't use for polonium electrical position.
no, the position. We take
Yeah, but this is like volcanic.
It's a good question. I cannot tell you at the moment about the sources that it can obtain. It was recent studies on on the stability of different resins in the ionizing radiation or medical applications. Then I can find the source.
Yes.
Our guys, but I don't remember the numbers.
Explain that you cannot keep the strontium on its recycle.
No.
We must move that. Remove after the
That cannot be used as a source then.
Yes. Because I think that the strontium will be destroyed.
Yeah.
Yeah, I know.
So all this process has to be dealt with in liquid phase.
Sorry?
It should be in the liquid phase.
For this process, yes, of course. For iron exchange, for solvent extraction.
So what's the application of the gas chromatography?
It can be used, but it's very limited application for, I don't know, very volatile compounds like tetroxide of osmium or iodine or some other very few applications for gas chromatography.
Not so much.
No.
Only
And
some-
again, with gases, you can easily contaminate equipment. To use something that you can remove easily, and they will not migrate on the long distances like gases.
the system in respect of how big it is.
Just for that, so it's not
Expensive.
everything now is expensive. All the equipment is equipment, they're all quite expensive. It's millions of rubles and tens, dozens, thousands of euros. For us, it's expensive. Yeah. For some commercial companies, it's expensive. Yeah. For measurement, in the first lecture, I showed you the spectral simulation, hyperspectrometry, or just ground spectrometry. So ground spectrometry can be used as well, and it can be used, for example, when you calculate the chemical yield, you measure the tracer that you add for this equation. Very often it is done in some tracer. Or even for strontium 85.
So in case you don't have this machine,
It depends on the amount of the radionuclides in your material. If it is, for example, in industrial plant, they measure enrichment not by hyperspectrometry or gamma spectrometry, but by UV spectrometry. Spectrophotometry, because they have a highly concentrated solution. But you cannot handle them in normal way. You have small cells with all these certifications. ICP, yes, but it is again mainly for long-lived radiant lights, because in this case we will have a low activity and high temperature mass. So you can look at previous lectures on this radioactivity very low, the relationship between activity and mass, and then the half-life. So if you have very long half-life, have low activity, even if you have very much mass. Yeah, for many radiant class short half-life, you can use only radioactive methods. For uranium, for example, you can use for uranium, thorium, 99 with millions of years half-life. So you can use but not for all the Okay. If there is no more question, now we can go for lunch break. Yeah, we'll come back at 2. It is dissolved in octanol, and then it has in a support, and you separate this solution. With octanol, with this so you separate the right the solution inside the box, and then you put the hard process. And that's the problem that in this countries the resins are bleeding. So with time, all this so they lose their efficiency because of the function.
Have you tried to regenerate
They're regenerating, but again, as far as the textile comes, it's step by step removing from the subject.
One of the last pictures I would take is you.
Okay,
Oh, okay.
It's not this one.
One of you. I like the chemistry you're discussing.
Fine.
Yeah.
I want to ask.
That's a note of chemistry.
Yeah, and you will have your presentation.
I couldn't ask to
Give me special want to see.
So can I?
Yes,
Should I signature?
Yeah.
Because of now Corona is too. Every single I said I have fever and this. We at home, the therapist came. Today I went and do the test. Even if normal problem, health problem, but because of Corona protocol, you are not allowed to go out. Maybe you are not experienced, but now when I call my clinic, how many people are living there? You should be in one room. Nobody should touch you. Till we come. Till we come at 4 o'clock. I call at 8:30 something. 4 o'clock. They come. So till we come, maybe they are actually. But it is 1 hour, 2 hours, 3 hours. Then professor told me that okay, home be at home.
I can
I
try to find
that first they do at 9:30.
articles about
Then
the review
professor
articles.
immediately recommended me no be at home. So I was at home and the therapist said it's okay and
Give my some of my time
morning I make the blood test.
Okay, I think we will
So
prepare also the
it is
list of,
2 months.
the
It will be
articles.
okay. You should follow Corona protocol.
I'll just-
From July to June.
But,
From June there is new variant of Corona. That's why there's new treatment. July very strict. So much prepared. Also because of the new variant.
Yes.
And it's, even though I took vaccine, but still then I have to follow. So if I get yesterday, I can sign.
Yes, yeah, but you can, you should choose between the methods depending on the methods.
I also discussed with Professor about the medicine course. The professor will tell me when
Okay, so
something is physical. Because I have been trying to follow him since last 11 months. Because last year was supposed to be done.
Yeah, I think we are talking about it.
пишу, да, ты зарегистрирован?
Да. In spring,
Yes.
we are talking with you by email.
Yes. You remember?
It's
Oh, okay. So, is it your colleague?
Yes,
Whom I communicated? I just described it by phone also, by email. So is it okay? I also didn't know professors because I didn't know the surname. I saw
In the after session, the philosophy being very abstract. Can we find the solution for this? Maybe advanced vectors or sports. I understood you said about the
We'll try.
Is this? But I don't have it. Because of the sun.
Yes.
Perfect.
In the morning it's okay. So try.
Yeah. Решим умалевать, значит, бахмулы.
So let's continue with the effects in matrices and final disposal of radioactive waste, high-level waste, of course, or speculative fuel. So first of all, we have to remember that all the interactions of ionizing radiation, it is first of all interaction with electronic shells. That means that we produce a lot of charges when the ionizing radiation goes through the material. But also there is a displacement of atoms, and that means that we produce not only atoms that are located not on its place, but also vacancies, and it changes the properties of the material. And this displaced atom, they are produced not only by the interaction of alpha particles or beta particles with atoms, but also by the action of the recoil nucleus, recoil atoms, that, as we remember, they have also very high energy, like 100 or 200 kiloelectron volts, and it's enough to displace atom from its place. So all these processes leads to different changes in properties of the material, and one moment, please.
I think that is Kerma.
Борис Федорович, добрый день. Я перезвоню сейчас на лекции. Нет, я вот читаю лекцию. Да, хорошо. So, sorry, what was the comment?
That's the definition of Kerma. Observed dose.
Yeah, it's absorbed dose that is measured by in grace. So it's the whole energy absorbed in the material.
I mean, that definition is Kerma in this metric.
No.
K-E-R-M-A.
No. Because Kerma is used only for non-direct ionizing radiation, for gamma rays and X-rays. For alpha particles, Kerma is not used because Kerma is the kinetic energy of the secondary charges, but we are dealing with the whole energy. So
It's Kerma.
it's absorbed dose. So the whole energy absorbed in matter, it's absorbed dose. Kerma is a specific term for dosimetry, but for non-direct ionizing radiation, like gamma rays and X-rays. Yeah, so again, this absorbed dose is 1 gray, and when we are talking about the consequences on material, on the solutions, or any changes in composition, we are talking about the chemical radiation field. And it can be measured in different units, like 1 mole per joule of absorbed energy, or it is ions per 100 of electron volts. So, but you can directly change between them. So it's quite simple calculations. But usually they use like a number of molecules produced by 100 of electron volts, because it's small numbers of one molecule, 2 molecules per 100 electron volts. Yeah, and just a relationship between different units. And when we study irradiation of the materials, it's a big question what we are using, because they have a different impact on the material, the type of radiation. So electron beam and gamma rays, gamma sources, they have more or less the same impact, because as we remember, so all the lectures, they are not for just for fun. The main results of the interaction of gamma rays with matter is the production of electrons. Yeah, as photoelectric effect, Compton scattering, they all produce the electrons. That means that the interaction of electron beams and the gamma source, they are all producing, again, electrons. So the effect is more or less the same if we irradiate by gamma source or by beta source. The only difference is the penetration depth of this type of radiation. Electrons, depending on their energy, can penetrate in a depth of few centimeters, let's say, if it is very high energy electrons, like several mega electron volts. And gamma rays, of course, they can penetrate to the depth of dozens of centimeters, let's say. So again, it depends on what is the volume of material we want to irradiate, what we have or what we can handle. For example, if it is like a matrix with the real high-level waves, and we would like to see what will be the changes after a certain dose. That means that we are working with the radioactive materials. We cannot use like a cubic meter this material, so it's small amounts, and we can choose which ionizing type of ionizing radiation we can use. Then heavy particles accelerators, it's another story, because it is like a model of how this recoil nucleus will affect on the properties of the matrix or another material. Again, recoil nucleus, it's a heavy particles, yeah, like rhenium or xenon or I don't know, radon or whatever. And with these techniques, heavy particles accelerator, we can simulate the action of this recoil nucleus on the properties, on the structure of the material. But the problem that the penetration depth of these heavy particles is only few microns. Even with high energy of these heavy particles, even with few megaelectron volts, the penetration depths will be only few microns. That means that we cannot use a bulk material, we cannot study the action of these heavy particles on the bulk materials. And we can only see the changes in the very thin layer. And it's always a problem when we study these irradiation effects. We can use, for example, internal sources of irradiation. So we can put in the matrix alpha emitters or beta emitters. They will distribute homogeneously. We can, but to reach the doses that we would like to reach, it's something like 10 to 18 grays. That means that we have to put a lot of alpha emitters. And it will be highly radioactive material, and we can prepare it, but it is very difficult to handle and to start to characterize them after irradiation. We can store it for a certain period of time, 1 year, for example. It will accumulate these high doses. But what to do next? Which technique we can use to handle this material? It's a big problem, and one of the way to another problem is that we have, for example, matrix for high-level waste, and we know that after 1,000 of years, the dose will be as high as 10 to 18 grays. But we would like to produce, we cannot wait 1,000 years to see what will happen. Yeah? We want to do it in 1 year, maybe 2 years, or even faster. That means that we put all this high amount of dose in a very short period of time. But there is also effect on the dose rate. So if you have very low dose rate, that means that the material itself has a time to relax and to become in initial state. So if you put if you have a very high dose rate, that means that material doesn't have this time for relaxing, and it is absolutely different effect on the final state of the material. So with relaxation or without relaxation, and but yeah, it's again a compromise because we don't have time to wait even hundreds of years to see what will happen. We have to use this high doses of radiation to see what will happen with material. So it is a compromise, but yeah, we have to deal with it. And also the problem when we have very high dose rates that we heat the material. And when the high-level waste are stored in for 1,000 years and the dose rate is not very high, that means that heat can be dissipated and there will be not very big increase in temperature of the material. But when we put the high high dose rates on the material, we will produce, we will heat it up very fast. So, yeah, it's just an assumption is what is 1 gray? Is it a big number or not? And we can easily calculate this heat production, the rise in temperature. That means immediate rise in temperature, and for water, 1 gray will increase the temperature of only 2 to 10 to minus 4 Kelvin, and it's not very big number. And also, if we have the heat dissipation, then we will have very low increase in temperature. But going back a bit for dosimetry and radiation effects on the human health, the lethal dose is around 10 grays for human beings. That means that the human body will be heated only to 10 to minus 3 Celsius degrees by receiving this dose. So it is called radiobiological paradox. That means that the energy itself is not very big, but it is lethal dose for the human being. And yeah, it's an interesting topic, but we will not go today in details in this. But if we again have a big dose rate, and we can recalculate it into the heat production, we will see it is an example of calculation for cement matrix. That if we will have a very big heat production, our material will be heated in the middle up to, let's say, 300 Celsius degrees. So for such materials as cement, it's very high temperature because it contains water molecules. That means that all the water molecules will be removed, and the properties of this material will be decreased, the mechanical strengths and other properties. But again, we have to use high dose rates. How to deal with it? That's the question in every certain cases. Also, if we have materials like cements that contains water, then we will have a lot of not only like amorphization of crystal structure, but also a lot of chemical processes inside the material. And this is an example of water radiolysis. We can see that there are many products. It's a very complex process, but for us, it is important that the hydrogen will be produced during the irradiation. Hydrogen is an explosive gas, and at least in Russian law, there is no gas evolution is allowed in matrices for high-level waste. So that means that cement materials cannot be considered as a matrices for high-level waste by the law, because they will produce hydrogen anyway. So, and it is forbidden for matrices for high-level waste. So another process is the degradation. Yeah.
May I interrupt? Or
Yeah, for sure.
so if H2 will be the highly sensitive towards bonds, but if it is a ionized form H plus or H minus or a single atom, then it's not sensitive towards bond. H2, yes.
Yes.
But when it is H plus or H minus, ionized form,
Yeah, but
or it's a
I will show you a picture later.
Ah.
So even here we can see not very nicely, but there is a time of radiation and the products. So so it was analysis of the products that are produced during the irradiation of cement, and this line, it's production of H2, the gas. Gas is produced during the irradiation of the cement. So it's not only H plus or H3O plus or whatever, it's also the molecular hydrogen. is produced during the irradiation. And you can see this experimentally calculated G value, that means the radiochemical yield of different species. And there are certain numbers, these molecules per 100 electron volts. And where's the hydrogen? Yes, on the first place. So it's almost half a molecule of hydrogen produced per each 100 electron volts of absorbed energy. So it's quite high activity, high concentration. Another interesting results on the properties of the cements, for example, that the porosity is decreased during the irradiation, and it is caused by this chemical process of formation of this calcium peroxide. It forms also further octahydrate of calcium peroxide, so it's additional mineral phases formation, and also the additional carbonization of this calcium compounds. So that means that porosity due to the formation of new phases decreasing, and it's quite interesting result. And this is again our experimental results on irradiation of cements of different compositions, and it is evolution of the hydrogen released from this species. So we can see the linear growth of, not linear, but this exponential growth of the hydrogen released from the cements, dependent on the absorbed dose. There is a limitation of this release because mainly only not free, but water molecules that are located in the pore space are degraded due to action of ionizing radiation. And again, this is an example of how different dose rates affect on the chemical, not properties, but the yield of it's total gas pressure, but it's mainly hydrogen pressure. So you can see the difference between the different dose rates. So it's when at least when you study the properties of the material, you have to state in the text which dose rates we use, because the dose rates itself will have a very important impact on the final properties of the material. Not only the total absorbed dose, but also the dose rates. Please note this. And this again quite interesting results that is related also to porosity. So porosity decreased with the absorbed dose, and due to this, due to the formation of new mineral phases, the mechanical strength also increased for cements due to irradiation. To a certain point, it will not increase to infinite values of absorbed dose, but at least to the doses of 10 to 6 grays, so 1 megagray, the compressive strength, the mechanical strength is increasing for cements. This is an example of high doses, so it's already 10 and 100 megagrays. It's not so first it's also maybe a slight change, but with these uncertainties, we can say that even to a dose of 100 megagrays, the mechanical strength of the cement matrix doesn't change. Yeah, 100 megagrays.
What happens if we add some
polymers will be decomposed, of course, at such doses. They will be burned. So you cannot use plasticizers in cement so it was investigation as a confirmation or evidence that in general, if we will not look on the gas release, all other properties of cements like compressive strengths, leaching rates, what else? Conductivity, thermal conductivity. With all these properties, cement matrices can be used for high-level waste immobilization. But the only problem is the gas production, gas release. Yeah, and also we cannot see any structural, big structural changes of the cement compounds before and after irradiation. Again, it is the example of how the leaching rates are changing due to the irradiation of cements. And again, we see a slight decrease in leaching rate. It means that due to the decrease in porosity space, due to the increasing in compressive strength, the leaching rate decrease because there is smaller volume or smaller surface area that is contacted with water, and that's why the leaching rate is decreasing.
Also, porous and permeability decrease. That's why.
Yes. And then, so it was about the cement matrices, and now we will go to the ceramic matrices. There is also an effect on the stability, radiation stability of matrices, depending on the size of the grains. Yeah. Yeah. This is an example of monazite matrix doped with plutonium-238 with a relatively short half-life, and it was synthesized around 20 years ago. So that means that after these years, it already accumulated quite high doses of alpha radiation, and these numbers are already similar to those that we can expect after around 1,000 of years of high-level waste storage. And after that, so it was almost 15 years of storage, and initially it was like a monocrystal of monazite with very nice surface. But after several years of storage, you can see the formation of such a flakes, and it was really interesting to understand what are these flakes, because in the crystal structure was remained the same for this compound. So yeah, even after 12 years of storage, the crystallinity was the same for the material, so it was not amorphized, and it was several studies by Raman spectroscopy, photoluminescence spectroscopy, by other techniques, and what we saw that the composition of these blisters, here it's called blisters, these flakes, is the same as the bulk composition of matrix, so it's europium phosphate but without plutonium. So it's somehow stratification, one can say, of the materials. So it was previously a solid solution, and now it becomes an individual phase of europium phosphate, but not monazite, but rhabdophane. It's also europium phosphate, but hydrated phosphate. yeah, it's so we use this transmission electron microscopy to see the structure, to have information about the structure of this material. And we saw this crystallinity crystalline phase, and it was attributed to this European phosphate. And you can see this not very nicely, but okay. Yeah. So you can see the formation of these cracks. So initially it was like a monocrystal, and with time, this radiation effect leads to the cracking of the material and the formation of this secondary phases. So, yeah.
Is there any standard or is there any booklets which can give an information about which kind of rocks and with respect to how much amount of radiation, what effect occurs? Is there any table or something like that?
There is some review on the different matrices, different effects on radiation on different matrices. I think you can find it. Yeah. Okay. We can also model all this system with the quantum calculations to see more in detail what is happening when we try to mix different elements in one matrix. And we saw that there is no deviations from the linear relationship between the composition and the parameters of this solid solution. So from theoretical point of view, even from some experimental point of view, it is not possible to see that europium and plutonium should be separated in these solid solutions. But in fact, due to the excess of energy, due to the radiation effects, we saw this separation of individual europium phase that doesn't contain any plutonium. It was nice work by John colleagues on synthesis of this mixed phosphate phases with plutonium and lanthanum, if I remember correctly, and they were able to synthesize the materials with the 20% of plutonium inside, but it was not possible to synthesize the homogeneous compounds with higher plutonium content, higher plutonium fraction. Plutonium in these attempts was present as plutonium dioxide. So it was a mixture of solid solution of lanthanum plutonium phosphate and also plutonium dioxide. So again, it's not totally understood now for a moment why plutonium doesn't want to be incorporated in this solid solution, because all the calculations, all the theoretical points in the beginning show us that it should be no deviations from these linear relationships, but it was not possible. Probably again due to the energy excess to the crystal structure and some effects of this. If we would try to irradiate mineral ceramic materials with very nice crystallinity to a very high doses, then we will see the amortization of these crystalline phases. So again, even for very nice monocrystal phases with high doses of radiation, it is not possible to remain it's not possible for them to remain as a pure crystalline phase. Either it will amorphous, amorphize, or it will be produce the secondary phases, some other compositions. And this is an example of so-called critical amorphization dose. So it is the temperature in Celsius degrees, and this is dose so it's alpha decays per gram, so 10 to 19 alpha decays per gram of the material. So what it shows us that at very low doses, absorbed doses, the material itself stay crystalline. At higher doses, it become amorphous. But if we irradiate the samples and heat it up, then we recrystallize it again to the crystalline phase. So amorphization is not let's say final state. You can it's not you can reverse this process back by heating the material. And knowing the critical temperature of the amorphization, you can compare the different materials. You can compare the radiation stability of different materials. The higher the temperature, the lower the stability of the materials. So because you need more the higher temperature to recrystallize it, so it's not so stable. And crystalline state or amorphous state is very important, because if you have amorphous solid state, then the leaching rate will increase, because it will have a higher surface area, more contact with water, and that's why a higher leaching rate of radionuclides. And this is one of the most important parameters for safety assessment of the final repository. And this is an example of the glasses that contains again plutonium 238. That is the initial state of this glass. So the color is attributed to the plutonium content. Without plutonium, it's more or less colorless. So plutonium gives this color. And also, it's interesting that it is, I don't know, can you see it or not? It is a self-glowing effect. So it is photo made in darkness, and so there's no other source of light but the self-glowing of this glass. And after leaching just in water at 90 Celsius degrees, you see how drastically changed the surface of this glass. Unfortunately, there is no picture, but for the glass that doesn't contain plutonium, there is no effect on surface at all. So the radiation effects, they have impact not only on structure or its nice properties of self-glowing, but it also has such a dramatic effect on the surface of glass. And it was found that this gray compound is concentration of aluminum and plutonium. So this light areas is plutonium atoms, plutonium compounds. And it was found that, or estimated that the main process that was responsible for such a behavior of this glass is a radiation of water in the near surface of this glass. That means the pH of the water is decreased in the very local area, and glass dissolved, and the secondary mineral phases are formed near the surface area. That's why it was not the case for the non-radioactive glass because there is no radiation of water, so no effect on the there was no effect on the surface. And there is also consequences of relative, not long-term storage, but storage of the glasses for several years, where we can see the formation of secondary phases due to the diffusion of elements and the formation of the crystalline secondary phases in glass. And it is bad for the glass because glass is good when it's totally amorphous. If there is crystalline phases inside the glass, that means that there are centers of local stresses, and glass become very. Yes, thank you. And yeah, it was studies on the glasses that stored at Mayak facility, and they saw that in some cases, not that in all cases, but in some cases, the glass really became a powder, so it's not anymore solid or monolith. And with all this matrices for high-level waste, we finally came to the disposal concepts for high-level waste. And for disposal, or for final disposal, every country decides by their own which host rock they would like to choose for the construction of the final disposal. It's not only the desire of the country, but also the accessibility of the host rocks. If you don't have granite or you don't have I don't know, clay rocks, then you cannot choose these types of rocks. And there are several aspects how to choose the suitable site. It's not only the properties of the host rock itself, but also the question of the public acceptability. So there should be no useful ores or natural resources in this area, because future generation can decide to use these useful resources, and they can find this final repository. So it will be bad for them, and we have to avoid such scenarios. Yeah. And again, it's just a reminder that when we are talking about the final disposal, we are talking about multivariate concept of the matrix, container, buffer, and the host rock itself, like it's a Russian boat. And it is a small text, but you will see it in the presentation. Here, I would like to stress your attention that there are a wide variety of different materials used for these barriers in the multi-barrier system, for matrix, for container, for buffer material, and for the host rock. And you will see here that for high-level waste in all the countries, there is only glass that is accepted as a final form for high-level waste. For intermediate level waste, there are different concepts. It can be also glass or concrete or some other matrices. But for high-level waste, there is only glass that is accepted in any country that deal with high-level waste. And the first step not really the first, before the construction of the final repository, an important step is the construction of underground research lab in the same area to understand the properties of the host rocks in real scale. There are several underground research labs in different countries, in Switzerland, in France, in Belgium, in Germany, in USA. So, and now there is an underground research lab that's under construction in Russia. Of course, the construction of such objects is not always accepted by public or even by government. And it was like a scandal story in USA when they stopped the project mountain because in USA the operators of nuclear power plants, it's not the governmental organizations, it's just a commercial, public, private organizations, and they have to pay some taxes to the special fund, and this money they are going for construction of the final repository of spent nuclear fuel. And Yucca Mountain, it was a project for such a repository. They spent several billions of US dollars since 1985. And in 2010, they just stopped this project due to some technical problems. And it was really a bad situation because all this money just goes for nothing. And they have to decide what to do next because after almost 30 years of investigation, they actually don't have any solution for already accumulated spent nuclear fuel. So yeah, it's a very sensitive question when we speak with public, and it's really, and sometimes it's really difficult. And there are several potential hotspots that are now, except the volcanic tooth, they are not anymore under consideration for potential hotspots. So these are crystalline rocks, means granites or gneisses, clay rocks, and salt domes. And different countries they are looking for different potential hotspots. And all of these hotspots, they have their benefits and drawbacks. For example, granite, it's very hard material, very stable for billions of years. But again, it's very fragile. If you just apply some stress on granite, it will form fractures. That means it is the pathways for water that can come to the final repository. But yeah, it's very hard material and with very nice properties. Clay rocks, it's an interesting material because clays, they have this self-healing effect. They can extend the structure. So, okay, so when they absorb water, they increase in volume, and that means that if there is a fracture and water coming in this fracture, the clays itself, they increase their volume and seal the fracture. So that's why it's called self-healing effect. That's why they have low water permeability, and clays itself, they have very good absorption properties. We have even this medicine that are made from the clays for when we have some poisoning of our body, we drink it, we use it for absorption of all this poisonous. And they have also very low solubility, but the problem that clays have very bad thermal conductivity, and also due to the action of the water, they form colloids. And colloids can be a potential migration pathway for radionuclides. So radionuclides can absorb on clays, they're good sorbents, and with colloids goes with the water streams. So, and salt domes, again, they have this self-healing effect because salt can be dissolved by water, but can be reprecipitated due to the saturation of this aqueous solution. So again, it will seal the fracture that can form. That's why they have low water permeability, but in wood they have good thermal conductivity. But even if there is low water permeability, salts are soluble, and that's the problem. For example, in Germany, they had this problem with the salt domes in Gorleben. Water starts to penetrate to these tunnels. Yeah, and in Russia, it was a choice for crystalline rock. It was quite a long story, and yeah, it's an example of granite in Switzerland. It's a nice test site. This research lab in mountains called Grimsel, because it's a Grimsel Lake, and it's a very interesting facility because initially this tunnel between two lakes, these two lakes have different height of the surface, and that's why there is a electric generation company constructed the tunnel, and the water going from one lake to another and produce electricity. And Swiss government decided to use this tunnel as a analog of underground research lab, because there is still 400 meters of granite above the tunnel. So you can construct the research lab underground, 400 meters underground, or you can use this tunnel that also has 400 of granite above. So the pressures, the conditions will be more or less the same, and that's why they use it. So I think it's very nice choice for the research studies. They made a lot of research on nuclide migration in these fractures, etc. So it's not really underground, but analog underground research lab. And this is an example of granites, gneiss from the wells from the site in Russia. The future repository is proposed, and it's just an example how different granites can be in composition and viewing their properties. So that's why we need quite a lot of research to confirm that this place is suitable for final repository. And this is just a map that can give you some information how far it is. So it's Moscow, and this is Krasnoyarsk, and this is city Zheleznogorsk. The final repository will be located. So it's quite far away from Moscow, fortunately, but not very far away from highly populated city of Krasnoyarsk, only 50 kilometers. Yeah, there's a map. So this line, it's the area of the closed city of Zheleznogorsk. Probably you know that in Russia we have several areas that are closed for public. So it is cities, quite big cities, maybe with 100, 200,000 population inside, and they are closed for public. That means that you cannot just enter the city. You have to order the special passes to come there. To meet relatives, for example, or for a job, I don't know. And this the selected site is located inside this closed territory. That means that there is additional protection against any, I don't know, actions, possible actions on this site. Previously, there were two sites that were also considered as a potential repository sites, Kamenny and Itatsky sites, but they're a bit better in properties. They have less fractures, for example. But finally, it was decided to use this Initiative site that is located inside this closed area. And again, we have this multi-barrier systems, matrix, stainless canister, buffer material that is bentonite clay, and this 500 of gneiss rocks, crystalline rocks. And as I told you, the selection of the site is quite a long story. In Russia, it started in 1992, so more or less 30 years ago. It was a geological survey of different sites through all the Russia. It was not only granites considered in the beginning. There were also clay rocks and even salt domes as well. But finally, only granite system was considered as a potential host rock. And in 2008-2012, it was detailed geological studies in this big area. And finally, they have chosen this Initiative site and prepared all the documents. So it was public hearings of the citizens of the Zheleznogorsk city, etc., etc. And then it was small correction, not small, but correction of the project, because yeah, initially it was planned that there should be two tunnels underground, and they should locate it 75 meters in height. And between them should be wells that would be filled with the canisters with high-level waste. But finally, they decided that it's not a proper way to store these canisters, and now it's another project. So now they started the construction of the surface facilities and started to bore the wells. Deep wells, so we'll see how it will work. So they should generalize all the research studies before 2030. But as we saw from international experience and from Russian experience, that most probably this date will be shifted to, I don't know, to 2035 or 40. And this is a map of other underground research labs. So you can see that there are quite a lot of different underground research labs in the world. So it's not the only one, not the few of them, but it's like dozens of different facilities dealing with studies on migration of radionuclides and studying the safety assessment of the potential final repository. Yeah, and before we talked about the matrices for high-level waste, but there's another design, another concept of open nuclear fuel cycle, when we directly dispose the spent nuclear fuel. And yeah, as we talked before, the first facility for final disposal will be constructed in Sweden. Yeah, and this is the design. So they put the spent nuclear fuel in these tasks, in these canisters made of copper. And there's another concept for final repository that is called deep wells. Deep means that they go not for 500 meters, but to 5 kilometers. And it is a well where you put the canisters one by one, to the height, for example, 3 kilometers. So we have 2 kilometers of well complete filled with the canisters, and then you close it and fill with, I don't know, cements or other buffer materials or whatever. So you have all the high level radioactive waste very deep underground, and maybe it will be very safe. So it's nowadays it's just a concept. So in general, we have techniques to bore such deep wells. It's not a really big problem, but the problem is the assessment, the safety assessment of this concept. So that is not done at the moment completely, let's say. So there is no country that accepts this concept, but I think it can be applied. So, and this is, I think, yes, all for this lecture. Now we can have a short break. Sorry, questions? Yeah. Sorry.
Okay, question one, just curious. You mentioned about the tunnel in Silicon between two lakes. You say that they are planning to use it as a sporting area. They are
not for this sport, but something for research.
for research, sorry, yeah. For research. Are they not using it anymore for, water testing?
They also use it for
So they're
energy production. They bought the additional tunnel. So there's a main tunnel, and they bought.
Okay, I see. And your last slide, you mentioned kilometers.
Yes,
speed.
5 kilometers.
So I missed some part, but maybe you already told it. What about the cost of going too deep, like?
As I saw from the publications, they estimate that the cost of such repository will be lower. Because you just need to work on the well. You don't need to work with tunnels or all these systems for people, because in Swedish concept, in Russian concept, or in Finnish concept, there is it's not fully automated process. You need people to work there. That means you have all this ventilation system, etc., etc. And here, you just need a well. So then it makes it more efficient for mechanics.
So we are discussing about the disposal, long-term disposal.
Yes, final disposal for.
What's the problem? Enrichment and so recycling and enrichment. There are different processes.
One of the point. So now all the concepts, at least I'm not sure about the Russian concept, but I saw that French concept and Swedish concept as well. They said that this final disposal should be constructed in a way that future generations can accept this repository. Not easily, but that they can extract all these containers with high level waste, or not high level waste, but spent nuclear fuel, because they think that future generation can handle these materials. So previously it was another concept that it should be closed, completely with so that nobody can access it. Yeah. But now it's a bit different. I'm not sure how they plan to do it. So I don't have this information.
So enrichment facility doesn't need some kind of things. Because they have to also be put somewhere, take it somewhere.
Again, Russian facility can handle this technical purification. Just for the moment, just a question of economics. It is more costly to reprocess technical fuel than just for the final. So that's why they think that future generation they will have such technology so that it will be more efficient economically to extract this technical fuel, reprocess it.
And use it, reuse it.
Any more questions? If not, then we can have a break now for 15 minutes. Yeah, let's say 20 minutes.
Okay.
Yeah.
Не, вот здесь микрофон.